So everything is where it should be, so we can start. No, the correction, it is 260 millimeters repressed, so we can start on your go. Step number 4, okay? Step 4, inaudible closed. Andrei, PHO hatches are closed. That's what Andrei reported. Okay, copy. Then we are sending command to the cover-deck valve, and it will be repressed to 260 millimeters.
Again, if you're just tuning in, just a few minutes ago, we had the hatch closure concluding today's spacewalk at 4:01 p.m. Central Time, and we had an elapsed time of the EVA of 5 hours and 14 minutes.
Could you please report the ODSK pressure gauge readings? 033 is on the ODSK. Okay, sounds good. Now it is 80. $120. And what is the MV pressure?
$150.
150 millimeters. Copy. And what about the spacesuits? 018 and 016 respectively. Copy. Guys, don't forget to use Valsalva and do the purge. Don't forget about it. Okay, copy.
Давление 200.
This pressure reading is 200. Copy.
$220.
220. Copy. Sounds good. The delta pressure is 006. Copy. So when it reaches 260 millimeters, you will have to close cover the SU valve. Okay, copy. 240. 240.
With the completion of today's spacewalk, we'll give you a little bit of statistics here from the International Space Station. Today was the 263rd spacewalk in support of ISS assembly, maintenance, and upgrades. It was the 6th spacewalk out of the ISS this year. It was the 4th spacewalk during Expedition 69, totaling 40. This was the 6th spacewalk of Prokopiev's career, giving him a total of 42 hours and 16 minutes of spacewalking time. This was the 4th spacewalk for Patelin's career, giving him a total of 26 hours and 45 minutes. Today's spacewalk, again, was completed after 5 hours and 14 minutes outside of the International Space Station.
So it is going to 260, very close. Copy. We are closing.
Again, this was completing today's spacewalk, gave us a total of 1,671 hours and 49 minutes outside of the International Space Station in the assembly, maintenance, and upgrades for the International Space Station, which is the equivalent of 59 days, 16 hours, and 49 minutes of spacewalking time.
Cover is closed. The stabilization period has started. Copy.
Again, today's spacewalk began at 10:47 a.m. Central Time. The duo was able to complete all tasks on their list, including the removal of restraints to deploy successfully the radiator that was previously installed. After successfully deploying the radiator, the duo was able to successfully integrate the hydraulic loops into the thermal control system for the Naoka module. After doing deployment, the duo were also able to complete 2 gap spinner installs on the European robotic arm. After completing these tasks, the duo also went on to do a get-ahead task where they completed the installation of 2 handrails. These handrails were installed between the Naoka module and the Prishal module. Again, today's spacewalk was completed after 5 hours and 14 minutes outside. Now with the Russian duo, ISS Commander Sergei Prokopiev and Dmitry Patelin back inside the Poise module, and the repress is underway. We will conclude our coverage here today. Again, this is Mission Control Houston.
envoy in our transit out to the moon. This is the crew of Apollo 13. Wishing everybody there a nice evening, and we're just about ready to close out our inspection of Aquarius and get back for a pleasant evening at Odyssey. Good night.
It was plagued by bad omens and bad luck from the very beginning.
13, we've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks.
It never really converged to the point where you felt you really had total control of what was going on.
Okay, stand by.
About the time you'd turn the corner, something new'd show up.
Okay, we've had a problem here.
By the time we came on duty, we were well aware that we had a big problem on our hands.
Can say again, please.
It was life-threatening.
Houston, we've had a problem.
It was not about landing on the moon in the right place. It was about survival.
Main beam, most wonderful.
Stand by 13, we're looking at it.
Saturn V building up to 7.6 million pounds of thrust, and it has cleared the tower.
This is Mission Control Houston. We appear to have a good first stage at this point.
Okay, Bada. We're go, flight. Looks good here. Guys, that's good, flight. Okay, Econ, GNC. Looks good, flight. Looks good, flight. Okay, Sergeant. Looks fine.
The crew was Jim Lovell was the commander. Jack Schweigert was the command module pilot. Jim I had worked with as a backup crew on Apollo 8. When he flew Apollo 8, I was the backup lunar module pilot on that mission. And then we worked, obviously, as a backup crew for Apollo 11. I backed up Buzz Aldrin on that mission. Jack Schweigert, because of a measles threat, replaced Ken Mattingly 2.5 days before launch. So that was something that never happened before or since, I don't think, on a mission.
Flight Dynamics Officer says the trajectory looks good. We show 1/2 mile in altitude at this time.
We had 4 teams in mission control. We did this from a standpoint of easing the shifting schedule, being able to train for very specialized events during the course of the mission. And then one of us always designated as sort of a lead. And basically the objective of the lead was to address any crises that come up to get your team off the console, and the remaining 3 teams would continue 24/7 support for the mission, as well as picking up a lot of the actions related to the getting the crew back home. I happened to be on console at that time, and we're just right at the very end of our shift. We're preparing for crew sleep period. And one of the last things you do is take a look at the cryogenics and see if you need to stir them up, make them uniform. So you got equalized pressures going into life support system and the fuel cells.
We've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks. In addition, I have Shaft and Trunnion for a look at the Comet Bennett if you need it.
Stand by. Okay, Houston, we've had a problem here.
Can say again, please.
Houston, we've had a problem.
Glenn was coming on with his team at that time, reading the log, preparing for handover.
By the time we got to handover, we knew full well that we had to take care of this thing in terms of an emergency. We were handling something that we knew was out of control. And in this case, every team that came on was dealing with a major set of problems.
I assume you've called in your backup ECOMs?
Flight, say again?
Have you called in your backup ECOMs now? See if we can get some more brain power in this
We
thing?
got one here.
Roger.
We had this loud bang, which kind of reverberated with a little echo, because the vehicles we're in were metal vehicles, and it was kind of like you're in a big barrel and they hit on the side with a sledgehammer kind of sound. In the tunnel area, some of the metal was actually crinkling, kind of like you take a Coke can and squeeze it, a little crinkling. So the two vehicles were moving, not together, but a little asymmetric, I think, in roll, and that was causing that stress in the tunnel area.
I went down into the command module and saw that we had lost 2 of our 3 fuel cells, that they develop oxygen. I then looked out the window and saw escaping at a high rate of speed a gaseous oxygen, and it turned out that that oxygen that I was examining was from the second tank, because the explosion occurred on the damaged tank, but that also ruptured the second tank. The first tank just blew the entire side of the spacecraft off.
Here is a bulletin from ABC News. The Apollo 13 spacecraft has had a serious power supply malfunction that could cause the lunar landing mission to be terminated early.
At the moment, the astronauts are continuing to try to isolate their trouble. The late report says the spacecraft now is operating on battery power alone. All unnecessary equipment is being turned off.
Oh, within a couple of minutes when I got to my position, from looking at the instrument panel, 2 meters had the needles on oxygen tank 2 in the bottom, and they were fed by different sensors, which are unlikely to fail at the same time. So I knew we lost tank 2. Without looking at mission rules, I knew that was an abort.
Here in Mission Control, we're now looking towards an alternate mission, swinging around the moon and using the lunar module power systems.
Although we spent lots and lots of time thinking through all the mission rules, when it really happens, like in this case, we didn't have to open any books to tell us what we had to deal with.
Tell me, you from flight. Go ahead, flight. I want you to get some guys figuring out minimum power in the LEM to sustain life.
Since the cryo-oxygen tank blew up, it ruptured the other lines, and we lost all oxygen supply to the fuel cells and the crew module. And the crew module was dying real quickly from lack of power other than the battery, and we didn't want to use the battery because we needed that for entry.
This is Apollo Control at 57 hours 46 minutes ground elapsed time. The black team of flight controllers is now on station in Mission Control Center looking at possible alternate missions, as we have an apparent serious oxygen leak in the cryogenic oxygen in the service module. And now in the process of powering down the command module. Less than 15 minutes remaining of electrical power to the CSM.
The biggest things we had to do in the dying moments of the electrical system in the command module was to transfer the guidance system from the command module to the lunar module. And we only had about 15 minutes to do that, because if we didn't get the guidance system in the lunar module, that meant that we'd have to start all over again to try to get the lunar module guidance system up to speed.
The scheme of going across to the lunar module, still connected with the open tunnel, the lunar module would serve as a sort of lifeboat for the crew of Apollo 13.
And then we started turning on all things, the control systems. We were starting to talk out from the lunar module. And in fact, we were in the lunar module before the ground realized it, and suddenly realized that, oh, they're over there. And then, of course, what they had to say is, we're going to have to get you off the course you're in now to get you back on the free return course.
And this meant that we were no longer on a path that would allow us to be swung around the moon and come back towards the landing spot on the Earth. The controllability of the spacecraft was okay as long as we had our indicators up, because we had practiced that, as I had said. But suddenly, to save power, we shut that down for a while, and we had to control it by only looking at our computer display. And I had never tried that before. I really don't know who had, and it's a very difficult task. And we spent a lot of our first part of our emergency or survival time just learning how to control the spacecraft in this mode.
The Paracynthian near the moon, they would use the descent propulsion system of the lunar module for trans-Earth injection burn at about 79 hours 30 minutes ground elapsed time. This would produce a day early entry at about 142 hours. That is a day earlier than a nominal free return entry. We're continuing to monitor the situation and still live on air ground.
No, I think to me the loss of comm was business as usual. Every mission, as you went around the backside of the moon, you had LOS and then AOS, and I didn't have any reason to figure we wouldn't be back in the communication when we came out the other side. I spent a good part of the time with Jack Schweigert primarily. Jim wasn't that interested. He'd been to the moon and seen it. We shot a lot of pictures. We had 2 cameras out and we were shooting pictures like crazy, like tourists.
We are about 70 hours from home, and we think we have the situation in control. We've projected the consumables as I've described, and we have a plan for carrying out the rest of the mission, but there's going to be no relaxation at all as far as that goes from now until splash.
Our first maneuver was to get us back on free return. The second one was to get us home early. The nominal flight time back home was 155 hours if we had done nothing else. But because consumables were critical, and the ground was calculating consumables, and Fred was also doing the back of the envelope type calculation, which he figured if we were lucky we had about 1 hour spare consumables left before we landed. We had decided, or the ground had decided, to burn at about 2 hours past the moon, at about 79 hours, a maneuver to shorten the time to get home again.
Plus X, Raj. We have ignition, Raj.
13%.
Ground confirms ignition.
40%. Raj, 40%.
Let's get it 40.
Houston copies. Stable control. Looks good now, fine. Raj.
Attitude looks good at this point.
Roger. FTP. Roger, FTP. Still stable.
After that, the ground was very much concerned with power, and we were too. Command module just slowly kept going down in temperature until I think just prior to reentry, it was down to about 38 degrees. And along with that, it was a sort of a chilling coldness. The walls were perspiring, the windows were completely wet, and it wasn't too healthy. I recall that we went in there to get some hot dogs one day, and it was like reaching into the freezer for the food.
One of the potable water lines was frozen the morning of entry on the last day. That's how cold it was in there, without active thermal control.
Of course, as the temperature went down, we became concerned about keeping warm, and Fred and I broke out our lunar boots, which we had stowed away in the lunar module, and Jack looked at his wet feet a couple times. But he had an extra set of underwear, so he put that on. We actually had a third little sleep restraint, which Fred then put on and buttoned up and kept a little bit warm.
The command module was very wet. The water separators weren't working, either in the LEM or the command module. There was water everywhere. In the LEM, there's no inner walls, so you could see water on all the connectors, wire bundles, plumbing, every turn of glob of water. And the command module, we actually had to get towels out to wipe off the instrument panel to see the instruments.
The carbon dioxide canister was filling up quite rapidly, and we had to figure out a way of using the canisters in the command module and place them in the lunar module systems.
And the ground read us up a procedure in order to adapt some of the command module canisters for use in the LEM. And as they read this thing up, Jim and I constructed one of these things. At this point in time, I think the partial pressure of carbon dioxide was reading about 15 millimeters. And we constructed two of these things and put them online, and I think within an hour, the partial pressure of CO2 was down to 2/10. So these were very effective devices.
About the time that we had the lithium hydroxide canisters in place running on the line, my team came in from the rest period. And the trajectory team came up. Jerry Bostic was running that, basically said, I don't know what's going on, but our trajectory is shallowing out. We had to figure out how to perform maneuver without a computer display system, and this was one procedure that they developed, I believe, for Apollo 8.
The ground, after some tracking, realized that we were not on a trajectory that would get us safely back home, and that we'd have to make another maneuver.
We're making the burn, and I'll give you a hack here at 2 minutes to go.
By this time, the crew stations became a lot different. There are 3 people in the lunar module now, usually built for 2. This last maneuver was going to be unique because we did not have the platform powered up, so we didn't have a normal method of determining the attitude of the spacecraft in order to perform the burn.
Right here, 2 minutes, we got it.
On Apollo 8, some time ago, we were concerned with perhaps losing a platform on the return voyage home, and since no one had ever made a lunar trip before, we were looking at sort of ways of determining how we could make these corrections home. And some of our people here at MSC had come up with an idea about using the terminator of the Earth to orient the spacecraft and then the sun position to get orientation and pitch. And with that knowledge, we could then make corrections to correct our angle of entry into the atmosphere.
And mark it 1 minute.
And as you know, I think that the angle of entry into the atmosphere is a very small angle, only about 2 degrees, and so it has to be controlled very closely, and that's what the main tracking is for. So at 105 hours, they gave us instructions to relight the descent engine, to orient the spacecraft in this manner, and give this particular procedure a try. And when they read up the procedure to us, I just couldn't believe it, because even on Apollo 8, I thought I'd never in all the world have to use something way out as this.
Engine arm to descent.
And because it was a manual burn, we had a 3-man operation. Jack would take care of the time. He'd tell us when to light off the engine, when to stop it. Fred handled the pitch maneuver, I handled the roll maneuver, and I pushed the buttons to start and stop the engines.
Ignition. Thrust looks good. Shut down.
470.
Okay, looks good. Nice work.
Let's hope it was.
Everything got stacked up to the end. We had a dead mothership. Another big challenge for the ground was to build the procedure in about 3.5 days, how to power it up. We had no procedure to power it up. It had never intended to be ever shut down. And that was a pretty monumental task for a lot of people on the ground.
We've run these simulators both here and at the Cape and at the contractors that continuously ever since last night. We've tried to simulate virtually everything that we've had the crew to do that is non-normal that they've done, and we've proven most everything that we've been able to run on the simulator prior to passing it up to them. There may be some details we haven't done, but at least we've checked the feasibility of everything we've done, and we'll continue to do that.
We really threw away the book. We had never powered down a command module in space, and we had never reactivated one.
And Jack wisely said, well, the first thing was to push in all the circuit breakers with panels on each side. And he said, let's punch in, we'll time it, we'll punch in 6 and stop and see if we smell burning wire, which you can tell when wire's burning. And then we'll step ahead and do the next 6. So we went through the initial activation that way, knowing things were wet. Now, we were, I think, saved in a second-hand way by the Apollo 1 fire, because they rewired totally both vehicles, so everything was virtually waterproof.
Normally when you come home, you have only the command and service module. So the only thing we have to get rid of is this service module just prior to entry of the atmosphere. Coming home now, though, we had a dead service module. We had a command module that had no power to it. We had a lunar module that was a wonderful vehicle to travel home with, but didn't have a heat shield, unfortunately, and shortly we'd have to abandon her.
And Jim and Fred were in the LEM and using the translation controller to give us some velocity, and when Jim yelled fire, I jettisoned the service module. And it went off amidst a lot of debris, which is usual, and Jim began to pitch around to try and photograph it.
We copied that report from Jim Lovell of service module separation at 138 hours, 2 minutes, 8 seconds.
I finally caught sight of the service module as it tumbled around in view. And it was, to me, sort of an amazing sight.
And there's one whole side of that big missing. Is that right?
I didn't realize that this whole panel by the high gain antenna was blown clean off right along the area where the panel normally swings open. I could see the interior. I couldn't see exactly what was damaged. I could see material hanging out from the interior.
Right by the high gain antenna, the whole panel is blown out, almost from the base to the engine. Copy that. It's really a mess.
So now we have the command module and the lunar module together, which is an unusual combination. We've never flown this before.
Then a little later, with an offset angle, we blew off the LEM, basically. We had to pressurize the tunnel and blow it off to get the separation kick of the LEM. And again, that was done very late.
We couldn't jettison that until we knew for sure that the command module was in the proper place, the proper time, the proper angle. If we came in less, we'd skip out like skipping a stone on water. If we came too high, we'd burn up just like a meteor in the atmosphere.
We're up now on 3 minutes until time of drogue deployment. Standing by for any reports of acquisition. Got a report that Orion 4 aircraft has acquisition of signal. Odyssey, Houston, standing by, over. Okay, we read you, Jack. That was command module pilot Jack Schwager. We're looking at the weather on TV, and it looks just as advertised, real good. It's been 2 minutes now from time of drogue deployment.
Apollo 13, this is recovery, over.
I recall, Captain, that when I spoke to you on the phone, you said that you regretted that you were unable to complete your mission. I hereby declare that this was a successful mission. From the start, the exploration of space has been hazardous adventure. The voyage of Apollo 13 dramatized its risks. The men of Apollo 13, by their poise and skill under the most intense kind of pressure, epitomized the character that accepts danger and surmounts it.
Once we were into entry, which was incidentally done fully automated, it was pretty much the normal entry all the way down, and all 3 chutes came out. And kind of miraculously, since we had abused the vehicle, the mothership, by freezing it for 4 days, the water tanks were frozen when they recovered it on board the ship. So we exceeded specifications on all the avionics, certainly. It gave us the second most accurate splashdown of the program. So it was a question of getting this entire world geared and oriented to one single job: get the crew home. And boy, the teams worked out great.
And it didn't need coaching. It just happened. And we all knew each other. We all were comfortable with who could do what and so on. So there you are. We pulled that off.
Actually, I guess when the parachutes came out and they blossomed and we landed on the water and didn't sink, I think we were home safe.
Well, of course, when we hit the water, we were very happy to be back home, and we commented on that fact. The recovery of 13 was almost textbook recovery. It was a calm day. The actual splashdown itself was very mild, and the Navy did a grand job.
If anything, has increased my confidence in the ability of this nation's space program to take an unusual situation and react to it and come out with a successful conclusion. I consider recovery of the crew a successful conclusion of it. But I have nothing but the utmost admiration for the people on the ground who work tireless hours to get us back.
Sometime this year, I'll have had 15 years with NASA, and I don't figure I'll retire for another 30 maybe. So I'll just do whatever job the agency decides is the best place I can be and to contribute the most.
Imagine if you were an alien who, was visiting the Earth for the first time from some other galaxy. Imagine only visiting the United States and never visiting any other part of the Earth's surface. That's essentially what we've done with the Apollo missions. Really been able to do wonderful and groundbreaking science with the samples, collected during the Apollo missions. But again, we visited only a very small part of the lunar surface.
The way that I think about it is it's the equivalent of landing on Earth and getting rocks from Kansas. It would give us insight into one particular location on the Earth, but not at all the diversity of what we see on the Earth, what we know is present on the Earth. So the ability to go to a different site, a different location, get different samples will just enrich what we've already learned from our Apollo samples.
There's a lot left to be learned about the moon, and it starts with the South Pole.
Artemis astronauts will fulfill a different mission in a unique environment. While the Apollo astronauts who visited the moon's surface between 1969 and 1972 landed near the equator, Artemis astronauts will venture to the moon's South Pole region, frigid, rugged, and with unique light and darkness conditions that make it an ideal location for exploration. The South Pole region is also home to the rim of the moon's largest, oldest, and deepest crater, called South Pole Aitken. It takes up almost a quarter of the moon, and is so deep it exposes portions of the moon's interior.
Yeah, the South Pole it's fascinating. There are some very unique types of rocks that are at the South Pole that will allow us to understand the entire history, not just of the moon, but potentially of the solar system.
Very early on in lunar history, we think that there was this increased period or very intense period of huge material hitting the surface of the moon, creating these really large craters or like giant holes, which we actually call basins. So getting a sample of impact melt from this basin would kind of help us bracket that early period of time.
The moon's South Pole region has resources that are vital for long-term exploration. Because the moon is barely tilted relative to the sun hovers over the horizon at the South Pole. Imagine a flashlight turned on, laying on a table. That's how the sun illuminates the South Pole. Light at the South Pole strikes at such a low angle, it brushes only areas of higher elevation, such as crater rims. These locations have sunlight for extended periods of time to harness for power. At the same time, the bottoms of some deep craters are shrouded in constant darkness. Scientists have measured the coldest temperatures in the solar system inside these craters, which have become known as perfect environments for preserving water for eons.
Over time, there's individual molecules of water and carbon dioxide and other gases that actually bounce around the surface of the moon. And when they get to one of these cold spots, they actually get stuck. So we call those places cold traps. And if you do that for millions and even billions of years, you can actually build up a pretty significant deposit of water and other ices.
From an exploration perspective, if we can understand just how much water there is and where it is and how to get it out of the regolith of the moon, we can turn it into really important things like drinking water for astronauts and even rocket fuel to take them back home. So really understanding these resources and how to use them is one of the objectives of the Artemis program, and it's what makes the South Pole of the moon so exciting.
We know the moon in incredible detail, thanks in large part to NASA's Lunar Reconnaissance Orbiter, or LRO. LRO has been circling the moon since 2009. It's the longest-lived spacecraft there. Through tens of thousands of orbits and data from 7 instruments, LRO has mapped the moon's temperature, geology, radiation environment, and is providing insight on how the moon is changing over time. LRO is led by Dr. Noah Petro, a planetary geologist at NASA's Goddard Space Flight Center.
LRO is this incredible mission. It was launched in 2009 as the opportunity to go back to the moon to create this three-dimensional, high-resolution, high-definition atlas of the moon. Where are there safe landing sites for human and robotic explorers? So what LRO is doing is really giving us the tools, the material, the data we need to make those missions successful.
For many years, LRO's elliptical orbit was closest to the moon during the spacecraft's pass over the South Pole. So scientists have more information about the South Pole region than any other region of the moon.
We know that we can do more and build upon the legacy of Apollo. But to do that, we needed a higher resolution data set. We wanted to know where the hazards were. We wanted to know where the geologic features were that we want to go explore. And so LRO has created that database. Incidentally, the LRO data volume is now over 1.3 petabytes. It's the largest volume of data that NASA has ever collected from any planetary body. It's remarkable. And what we've done now in support of Artemis, in support of other NASA missions to the moon, is we've created special maps. We share them with the public and we share them with the various engineers and scientists who are going to help enact and make Artemis a reality.
You know, there's basically a Google Maps of the moon, taken from pictures from the Lunar Reconnaissance Orbiter camera, and you can just zoom in and see a 5-meter boulder on the surface of the moon. That's just crazy. I could spend all day, and I have spent all day, sometimes just browsing around different parts of the moon, just looking at air rocks.
This wealth of information will make it easier to find ideal locations for a NASA base camp, and to quickly identify scientifically interesting areas to visit nearby.
So it's my real belief that we have an opportunity with Artemis to do something different than Apollo. We build on Apollo, we learn from Apollo, but we want to expand what Apollo was able to do and build this presence on the moon that is more than just 3 days, more than just 6 individual missions, but a much larger program that eventually will result in the ability to go onto Mars.
Mars is quite a bit longer away from our own planet than, of course, the moon is. It takes several months in some cases to get to Mars, and it's therefore going to be really critical when we have astronauts walking around on the surface of Mars to be able to stay there for longer periods of time. You've just spent 6 or so months to get there. You want to really be able to explore the surface around you, and having the ability to live off the land and know how to conduct exploration for longer periods of time is going to be critical for Martian exploration, and lessons learned for that sustainable type of exploration start right here at the moon.
So there's still so much for us to learn from going back to the moon from a scientific perspective. It's a no-brainer in my head. So with Mars in the horizon as our kind of end goal, this is an important step for us to take. And then also just kind of from a human aspect, we all have this kind of intrinsic desire to explore. I think it's in all of us and certainly in us as a society. And so I think setting our sights on something and accomplishing this goal together is really important just for international relations, for, you know, just coming together as a humankind, you know, the human spirit. I think that's a piece of what we're doing that we can't ignore as well.
I have 3 kids, aged 10, 6, and 2. I talk about space often with them. The great thing that my parents did for me was let me find my path. I also look at my daughter and I think, okay, Amelia, you know, she keeps saying she wants to be a firefighter, a construction worker, and an astronaut. And I said, well, Amelia, you can do all 3 and be an astronaut. Well, I mean, when you're an astronaut, you got to learn how to fight a fire in space. You got to learn how to build stuff. So you got to do all those things. What they'll become, I'm so excited to find out. But I have no idea what they're gonna end up gravitating towards.
So why is the moon my favorite body to study? I think growing up, you could always see it in the sky. You could see some beautiful stars and maybe Mars or Jupiter as like small little dots, but the moon is just there in all its glory. It's like our nearest and dearest neighbor, and you can even with the naked eye, you could start picking out features on the moon. I think that was really cool. You know, this is thousands of miles away, and you can still kind of be a geologist from the ground if you want to, and I think that's really cool, and that's why I always wanted to study the moon. Just seeing people walk on the moon, on this foreign planetary body, you know, looking at images like the one behind me here, I think that always blows my mind.
I will say with my 2-year-old, what I have noticed recently, and this is wonderful, is that when he sees the moon, we're out for a walk, we're driving around, or outside a window, we go, moon, moon. And just the fact that he can look up and see, oh, moon, moon, that makes me so happy.
Greenland. A massive ice-covered island in the northern Arctic, a land of pristine waters, enormous glaciers, and ancient geology. And for some, the site of a hotly contested claim of the oldest signs of microbial life on Earth. Meet Dr. Abigail Allwood, astrobiologist at the NASA Jet Propulsion Laboratory. Dr. Allwood is here in Greenland to investigate recently published findings of possible stromatolites, or microbial fossils, dating back to 3.7 billion years ago.
It's always when I go and see some rocks and outcrops in the flesh, it's so much more eye-opening and informative than it is to read about them in papers. And absolutely the case with this one. When I came to see them after that paper was published, I very much doubted that interpretation, and I thought, well, we need to do two things. One, we need to put a paper out, and secondly, we need to do a workshop and bring a lot of people out here to also see what their opinion is, reach some sort of a consensus on what the right interpretation was.
Extraordinary claims require extraordinary evidence, and a finding like this requires further investigation. Dr. Allwood has gathered a team of astrobiologists and will now travel by helicopter into the wilderness of the Ishua Greenstone Belt.
So we're out here to study an outcrop that there is some controversy over. There is a group of authors that has made a claim that there are biosignatures in the form of stromatolites in these rocks. And there's another group of authors, I happen to be one of that other group of authors, that has refuted that claim. So we're out here in Greenland to study those outcrops in more detail and to try to get a sense of the geology that surrounds those potentially stromatolite-bearing outcrops and try to get a sense for what the ancient environment looked like at the time that those rocks were forming. The claim was such a big deal because if it proves to be true, then this pushes back the earliest signs of life in Earth's geological record by a couple of 100 million years.
It means that the window of opportunity for life to emerge doesn't have to be very big. You know, literally, as the last bombardment is occurring, that you can say that life can take hold. At least our one example that we have that life took hold. Go to Mars. It means that it only also had to maintain its conditions, its sort of cradle of life, its opportunity for life to emerge for that short period of time. It didn't have to sort of maintain it for a couple 100 million years longer.
And when you go back to those very old rocks, they're usually altered and deformed, and it's very difficult to find those signs of life. But those are also the most interesting rocks to look at because we don't know when life originated on Earth, and we don't know what that earliest life was like. So the record that we have from geology is in these rocks that are very difficult to interpret.
Sorting out which way I'm going to put it. Okay.
Sampling here in Greenland is, it's not all that different from sampling anywhere else. A geologist's tools are kind of the same no matter where you go. You need a hammer, a chisel, a little, hand lens to look at the rocks up close, field notebook, camera, and you record your observations, and when you think you've zeroed in on a piece of rock that might be worth taking back to the lab, you get your trusty rock hammer out and just start banging away until the sample comes out.
When we're looking at rocks, trying to understand if they preserve evidence of life, we look for things in the rock that cannot form without the influence of life. They can change the chemistry, and they can actually change the shape of the ground. And they can make things like peaks and domes that are sometimes unique to the biology.
again, I think here what you need to do is look at the context of the rocks around those stromatolites and try to get a sense for what that geology is telling you.
This is our sample here, came from the outcrop. We've got that nice sort of cut and polished face there. And if it was really a cone-shaped structure, then you shouldn't see it on the back of the sample. You shouldn't see it in the back of the hole there. That's about 14 centimetres depth hole, and you're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. Got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front and it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what happened in the rocks. Part of making that story, though, is understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.
The rocks that we're looking at here in Greenland are similar, if not identical, in age to the rocks that we're going to be exploring with the Mars 2020 rover. We'd like to think that we can use the lessons that we take from studying the Earth's geological record and apply them when we start exploring the geology of Mars.
One of the really interesting things about searching for life on other worlds is, as a scientist, I have to actually, when I'm looking for life anywhere, I have to actually have a model of what I'm looking for to help guide my observations. And so by looking at these places that are very difficult to interpret on Earth, we get that practice and experience of how do we look at something and what are the questions that we need to ask and what are the observations we need to take to be able to answer them.
Any claim that is made about a biosignature on Mars is going to be debated. So I think that this workshop gives us an opportunity to exercise our ability to have civil disagreements over matters of scientific importance, because I think we're going to be doing much of that with the data that comes back from Mars as well.
I think seeing the rocks in the flesh is just so important. Can't do that for many people, so I think the next best thing is to try and recreate that in a virtual terrain sort of field trip kind of thing. That's what we're trying to do.
So OnSite is an application that we developed for the Mars Science Laboratory mission to help the science team that works with the Mars rover understand the context of the environment around the rover.
And it provides scientists the ability to basically meet on Mars. So it's taking Martian data down from the rover and using photogrammetry to stitch it together to create a 3D model of the outcrop. And then scientists involved in the mission and engineers as well are able to use that 3D model, enter the terrain and make decisions with a much better understanding of the context. We're also using LiDAR imagery out here, which is something not available on Mars. So that's using a laser scanner to basically three-dimensionally scan outcrops and get higher fidelity data so that we can get some very accurate information.
Yeah, so this is the map of the primary outcrops and the laser scans. This is the A outcrop here. There's the flag, there's the cut of the rock, and the other cuts. Now on Mars, it's a different scenario because we're limited to the instruments on board the rover. The rover doesn't have LiDAR. It'd be great if it did. So all we have are the 2D images to work with. 3D reconstruction from 2D images has been part of the Mars missions all the way back to Pathfinder in the late 90s. But it's always been on a per image basis from one rover position. So one of the innovations of in OnSight is we started combining rover imagery from multiple rover positions. So if the rover is parked next to a rock and the next day you drive around the rock, you can take imagery from those two positions and get a more complete model of that rock than from any one position, on its own. And the holy grail of this is to take all of the rover drives from landing to the current position, register them all together so you could walk from the landing site to the current rover position, seeing high quality 3D imagery all the way. So OnSight was started in the context of the Mars rover missions, but the capability that OnSight and tools like it provide is really, it's a virtual presence and situational awareness in an environment that's hard to visit. Mars is an extreme example of that, but where we are today in Western Greenland is not quite as hard to visit as Mars, but it's certainly not easy. So you can imagine geologists going into the field to these remote locations and bringing back not only their written field notes and photos, but a 3D capture of the environment that becomes kind of an immersive field notebook that they can revisit, they can share with their colleagues and with the public and help to communicate what that environment is like in a way that's really hard to get without actually being there in the field. So I don't think this technology ever really replaces a human in the field. Whether or not humans will go to Mars is not my expertise. But if and when humans do go to Mars, only a select few will go to Mars. But with this kind of technology, they can bring along experts from Earth to extend their knowledge and share that experience with the public, so the whole world gets to go along, for the ride.
So I've never been here before, and the landscape in this environment is just, my mind has been blown being out here for a couple of days. I mean, the scale of the glaciers, the complete lack of vegetation in this area, other than sort of, lichens and moss. It's just it's kind of an otherworldly place. It's really starkly beautiful. I think in terms of why anybody should care about these rocks, I mean, they are the record of some of the oldest processes occurring on our planet. I mean, there are very few places that preserve rocks this old, and so they're really a precious resource for geologists to understand what was going on the Earth, close to, in its infancy. So it's an important and special place.
I will gain a huge insight into these particular rocks, but it will also increase my understanding of how you actually demonstrate that something is or isn't a biosignature that I will apply in all my other work.
It's the ability to minimize the ambiguity before it even gets to the publication, minimize the ambiguity and minimize the bias. When it gets out into the press, it's going to be that much more considered, that much more robust. I think that's what's the best outcome of this workshop.
To observe with Hubble, we actually have to plan out pretty far in advance. And for the outer planets, what we do is we pick the time when they're at opposition. And that means that it's opposite from the sun, from the Earth's point of view. And that basically gives us the highest resolution view. That's when Hubble is the closest to each planet, even though that doesn't vary much over a year. And the planets are a little bit more challenging because they move. And so Hubble has to find guide stars first that tell it where it's pointing in the sky, but then it has to track those planets. So it has to move following the planet across the sky. And so that has to be interleaved with all the other science program Hubble's doing every single day. And so it's very carefully coordinated to fit in as Hubble then orbits around the Earth. And so it gets planned out down to the minute of exactly which image we're going to take in which filter for each of those planets. So it's a cosmic dance of getting Hubble pointed in the right place, moving in the right direction, and tracking all at the same time. The OPAL project, or the Outer Planets Atmospheres Legacy Program, is an observational program using the Hubble Space Telescope. And what we're doing is we're looking at each of the outer planets every year so that we can build up a time base using the exact same facility and the same instruments, so we can actually track what's changing over the years on each of those planets. And it started really with Jupiter. In essence, we were trying to look at the weather on Jupiter. And as we're trying to understand weather, we know even here on Earth it changes every minute, every hour, every day. And we didn't have that kind of time coverage, but we also didn't even have long time coverage to look at things that changed over seasons. And so we had this big gap in our knowledge where we just weren't getting frequent enough data to be able to trend any of these things. And the idea kind of came about to look at a legacy program where we built up a legacy for Hubble within the planetary community. And in 2014, we started with our first observations of Uranus. And the first thing I think we noticed was Uranus had a very prominent polar cap. It was very much brighter and getting brighter over time. We've watched it over the last few years get much brighter. Neptune, on the other hand, has been really quite interesting. The first thing we noted was it had a lot of bright white clouds, and they were coming and going pretty rapidly in a lot of different latitudes. And so when we start looking at Neptune and Uranus as dynamic planets with changing atmospheres, weather, like we know now for Jupiter and Saturn, we realize that we have a lot of gaps in our understanding. And so we've been able to use the OPAL program to track how much cloud cover we have from year to year. But the other thing we can do with Hubble that we can't really do any other way is look for dark spots. And so the Great Dark Spot was this big iconic feature we saw with Voyager. And when we looked again a few years later, finally when Hubble was online, it was gone. And that kind of surprised us because we were used to the Great Red Spot, which doesn't go away. It's changed over time, but it's still there. And so these storms are not quite the same as what we see on Jupiter because they form and go away on much more rapid timescales. The latest image of Neptune is really interesting to me because we don't see those bright white clouds we've been seeing the last few years. As a matter of fact, the only thing we see in that particular image is this great dark spot. And so in a lot of ways, it brings us around full circle because this looks so much like the Voyager image from 1989. And that was pretty surprising to me, not to see as much cloud activity as we've been seeing in previous years. The OPAL team is actually a fairly small team. There's only 3 of us, but our data is immediately available to the public and